assign you homework assignment number 1. In this assignment, I need to give you a few questions, relatively hard, but we need to use these examples. Okay, yeah. So you need a background of these examples, okay, for those questions. So let me start question 2.5. Okay, yeah. All right. Show that n to the dth power belongs to little o of exponential function a to the nth power. Yeah. Here, in order to make this question relatively simpler, I make an assumption d greater or equal to 1, and then let us assume d as integer first. Later, we will remove this assumption. Yeah. First, let us consider d as integer first. Yeah. And then later, we can remove this assumption, integer assumption. Okay. All right. Yeah. So here you can see this function, n to the dth, it's a power function. It is a power function. The variable n is the variable. It's a discrete variable, but variable at the base. The exponent is constant, so it's a power function. But this a to the n, it's exponential function. Variable at the exponent. The base is a constant, a greater than 1. Yeah. So these two different functions. Yeah. And here, we want to use the L'Hopital's rule. L'Hopital's rule. Calculate derivatives. L'Hopital's rule. Okay, yeah. All right. So here, we assume d could be any integer, any positive integer. Yeah. But later we will remove this assumption. Okay, yeah. This in my proof here, let's say for the simpler version, we make this assumption, integer assumption. Okay, yeah. All right. Now, let me show the work. How to apply L'Hopital's rule. Because for little o, we need to calculate the limit, the ratio of two functions. Yeah. Yeah. But when we apply the L'Hopital's rule, remember, we need to change the discrete variable to continuous variable first. So here, let's write a continuous version of these two functions directly. Okay. So we can take derivatives. X, we use x to replace discrete variable n. So we can take derivatives. Yeah. All right. But when we take derivatives, we need to check the indeterminate form, right? So no problem, because this is a infinity over infinity indeterminate form. So we can apply the L'Hopital's rule. Okay, yeah. Then the formula, the numerator derivative for the power function. Yeah. Formula, d times x to the d minus 1 power. That's the formula for the power function. Okay, yeah. Derivative of the denominator, another formula, natural log of a times the original exponential function, a to the x. Yeah. All right. So that's the first time we apply the L'Hopital's rule. After it, can we get the answer still? Not yet. Still, we cannot see easily the answer. Yeah. But it is still another infinity over infinity indeterminate form, right? Yeah. That means we can apply L'Hopital's rule another time. Second time. Take derivative the second time. numerator and denominator. Yeah. The second time, d minus 1 this time. And the dx to the d minus 2 power. D minus 2 power. Okay. And denominator natural log of a squared times a to the x. Okay. All right. Still, if d minus 2 is a positive integer, we need to apply L'Hopital's rule another time, and so on. Keep applying L'Hopital's rule until it's not an indeterminate form. If it is an indeterminate form, we always need to apply L'Hopital's rule here. See? Yeah. So let's assume we apply L'Hopital's rule all the way to the last one. Okay. Which one is the last one? Okay. Yeah. First, d factorial. And when you look at the variable part, x to the d minus d. D minus d is 0, right? D minus d is 0. X to the 0, that's 1. 1 is not a variable, it's a constant. When the numerator becomes a constant, it's not an indeterminate form. That means we should stop. So we get to the point we need to stop. We can stop at this point. Okay, yeah. And denominator, because we apply the L'Hopital's rule d times. So natural log of a to the dth power. All right, yeah. So then let's simplify this expression. Numerator is a constant, d factorial constant. Denominator, natural log of a to the dth power times exponential function a to the x. It's another indeterminate form, and we can see the limit immediately because the denominator goes to infinity. A numerator is a constant. Denominator goes to the infinity. Okay. So the answer is 0. The answer is 0. Okay. Yeah. So for this continuous variable version, the ratio of the two functions, its limit is 0. So we can go back to the discrete variable version and to the infinity and to the d's over. Oh, this time we need to use n. Okay, also 0. Okay, yeah. So it's legal. We can move from this continuous variable version limit to the discrete variable version limit. The reason I explained last time, because how do we approach to infinity? How do we make our x variable approach to infinity? Anyway, right? Yeah. The way to go to infinity anyway should be correct here when we look at the limit. Anyway to the limit. Here we just take the consecutive integer way. Okay, consecutive integer way. That's legal. So we can get this discrete variable version. So that gives us this little o asymptotic notation. Little o. Okay, yeah. All right. Now we complete the proof for this one. Yeah. After we complete the proof of this one, yeah, we can modify. So this d is not necessary integer. That could be any positive real number. Positive real number. Because if it's not integer, we can find it must be between two adjacent integers, right? You can find it must be between two adjacent integers. Yeah. Then can you get it? Then you only need to do some small adjustment, then you can get it. After you know it is between two adjacent integers, then you apply the result of this question, you can get your answer quickly. Okay? Yeah. Think about it. Yeah. Not that hard, not that hard. Okay? Yeah. Not that hard. Yeah. So if you like me to say a few more words, yeah, I just use 2 minutes. I can show you how to get that. Okay. Yeah. All right. Yeah. So if D not integer, okay, D is not integer. Yeah. If D is not an integer, yeah, then we can find an integer k such that k less than D less than k plus 1. How about that? Okay, it must be between two adjacent integers. Okay, it must be between two adjacent integers. Okay, all right. Now we use these two results, we can get the answer. Okay, so one result, n to the k plus 1 is in big O of a to the n. That's just our integer version of this question, k plus 1. Okay, all right. Second result, can you see n to the d belongs to big O of m k plus 1? Can you see that? Okay, can you see that? Right? Yeah. To see that, it's very easy. When we write the limit n to the d over n to the k plus 1, you do cancellation. The numerator is 1, denominator is k plus 1 minus d. We know this is a positive number, right? Positive constant. And to some positive constant, so the denominator should goes to infinity. Numerator is 1, denominator to infinity, so the limit is 0. If the limit is 0, we get this little o. Okay, can you combine these two to get this n to the d in big O of a to the n? Yeah, combine these two results. Yeah, right. Yeah, so you can get that. Yeah, right. Yeah, so n to the d, when you comparison with n to the k plus 1 already in big O, and n to the k minus 1 comparing with the exponential function, another big O, little o, yeah. So there you compare with the larger a to the n, even smaller, right? Yes. So yeah, because actually you do this. N to the d, if you compare with the exponential function directly, this time you do this. The product of the limits, okay? N to the d over n to the k plus 1 first. And the second limit, n to the k plus 1 over a to the n. How about that? The product of these two limits. And we know both limits 0. 0 times 0 equals 0, right? So we prove it. By calculating this limit, we prove it. Okay, so when d is not an integer, so we can use our integer result, we prove it. Okay, but this time we do not need to apply L'Hopital's rule. Yeah. Although we can, if you like, we can apply L'Hopital's rule, but we won't have factorial, right? Because that d not integer, how do you define factorial when d is not integer, right? You won't have that factorial thing. Okay, so that's why we try to avoid L'Hopital's rule, because we don't know where to stop, right? Yeah. There is no factorial, so we don't know when do we stop, right? Yeah. How to stop? Okay. Yeah. All right. Yeah. Yeah. Okay. So now we finish this question completely. Okay. We finish this question completely. Yeah. All right. Yeah. Yeah.